In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about multibody dynamics module in capsule multiphysics simulation software. Today I want to go through the rotational prescribed motion. Rotational prescribed motion is available for the hinge joint, cylindrical joint, screw joint, planar joint, reduced slot joint, ball joint, and slot joint features. The theory for rotational prescribed motion is similar to that of translation prescribed motion. The difference is that the rotation or angular velocity is prescribed instead of displacement or translational velocity. For the ball joint and slide joint features, relative motion is possible in all three directions. You prescribe the motion using a rotation axis and the magnitude of the rotation and angular velocity about this axis. The following constraint is added to the ball joint and slot joint features to prescribe the relative rotation in a joint, such as we have equations BR is equal to sinus of phi p divided by 2 multiplied by EAP, where phi p is the magnitude of the prescribed relative rotation and EAP is the axis of relative rotation. If a relative angular velocity is prescribed, an extra equation is added to find the relative rotation by integration of the relative angular velocity. We have a derivatives of phi p based on the time is equal to omega p, where omega p is the prescribed relative angular velocity and phi p is the angular velocity integration variables. Evaluating reaction force for the prescribed motion by selecting evaluate reaction forces in the reaction forces settings section of the settings for prescribed motion has several benefits over evaluating it using joint forces and moments computed by using weak constraints. The first one is that it includes the contributions of springs, dampers, and frictions applied on the joint. It works even if there are redundant constraints in the system, especially in a rigid body system, since joint constraints can be applied in the weak form in such a system. It is computationally more efficient as it adds fewer degrees of freedom. The next one is theory for applied forces and moments on joints. The applied forces and moments feature is used to apply forces and moments on all types of joints. It can be applied at the source of destinations, joint attachment, or directly to the joint degrees of freedom. When the load is applied directly to the joint degrees of freedom, the virtual work contributions added depend on the joint type, with a scalar force F for joints with one translation degree of freedom U, prismatic, cylindrical, screw slot, reduced slot. We have a F delta U with vector force F used in the planar joint, which has two translation degrees of freedom expanded into a global relative displacement vector URF multiplied by delta UR. This means that the component of VF, which is orthogonal to the plane of the joint, translation is removed with a scalar moment M for joints with one rotational degrees of freedom, theta hinge, cylindrical, screw, planar, reduced slot. We have a M delta theta with vector moment M for joints with three rotational degrees of freedom represented by the quaternion IRBR ball slot. We have a 2 multiplied by 0 M multiplied by RRBR multiplied by delta RRBR. The theory for applying forces and moments on the attachments is the same as described in the rigid reconnector section. In the structural mechanics module user's guide, the links to sections describe an external guide such as the structural mechanics module user's guide don't work in the PDF, only from the online help. Theory for friction in joints. The friction feature is used to add frictional loss to a joint. It is available for prismatic joint, hinge joint, cylindrical joint, screw joint, planar joint, and ball joint. The friction force is modeled using a continuous friction law, which is capable of modeling a sliding sticking phenomena. A strict application of Columbus law involves discrete transition from sticking to sliding and vice versa, as indicated dictated by vanishing relative velocity. This discrete transitions cause numerical difficulties, and to avoid them, the friction force is approximated with a continuous friction law. Ff is equal to minus micro n nu divided by absolute nu 1 minus exponential to the power of minus absolute nu divided by nu is 0, where F is the friction force, micro is the friction coefficient, n is the normal force, nu is the slip velocity, and nu 0 is the characteristic slip velocity. The term is 1 minus e to the power of minus absolute nu divided by nu is 0 is called the regularization factor. The regularization factor smoothes the friction force discontinuity. The characteristic slip velocity should be chosen to be small in comparison to the characteristics relative velocities encountered during the simulation. The continuous friction law describes both sliding and sticking behavior, that is, it completely replaces Columbus law. Sticking is replaced by creeping between the contacting bodies with a small relative velocity. The exact interpretation of the friction model for each joint type is described in the following. In general, an expression for the friction force such as Ff is equal to minus minimum micro n plus FAR and FAF maximum U print divided by absolute U print multiplied by 1 minus e to the power of minus absolute U print divided by nu 0 is used here. FFR is the additional sliding resistance. FFM max is the maximum friction force, and U print is the relative velocity in the joint. Since the joint are abstractions, there is no unique way to define the normal force and to which the friction force is proportional for each joint. There are several available methods for computing n, and you must select the most representative one. Friction can only be applied to the joints in the time-dependent analysis. Now I want to go through the prismatic joint friction force. The total friction force is defined as F is equal to minus minimum micro n plus FFR and FF maximum multiplied by U print divided by absolute U print multiplied by 1 minus e to the power of minus absolute U print divided by nu is 0. The total normal force can be computed from joint forces, interference, feet, or the combination of these two. Normal force case 1 contribution from joint forces. Case 1 1 normal force computed from the attachment reaction forces. For example, we have N is equal to sigma absolute FR multiplied by N, where FR the reaction force on the attachment boundaries and N is the surface normal in the deformed state. Case 1 2 normal force computed from joint forces and moments. N is equal to absolute Fj minus Fj multiplied by E plus I11 Maj 11 plus absolute R 12 and Maj 12 plus absolute R 13 Maj 13 and so on, where Fj or the joint force is the joint axis, Maj arm J1I are the components from of the joint moment in joint local coordinate system, and I are contribution force factors given by the user. Case 1 3 normal forces computed to joint forces in a specified direction, such as n is equal to absolute Fj minus Fj EE multiplied by R source E n is 0, where n is 0 is the direction given by the user. R source represents the rotation matrix for the rotation of the source attachment. This method is available only in the prismatic joint. Normal force case 2 contribution from interference feed case 2 1 normal force defined by pressure and contact area. N is equal to PR, where P is the contact pressure and R is the contact area. Case 2-2 normal force defined by the total force. N is equal to Fn, where Fn is the total normal force which are work and power loss. The ratio for contribution from the total friction force is obtained through a multiplication by the variation of the relative displacement between the two parts. Delta W is equal to Ff multiplied by delta U. The energy dissipation rate caused by friction can be written as Qf is equal to minus Ff multiplied by Up. Hinge joint chapter, most of the theory is the same as For prismatic joint, any differences are described here. Friction moment. The total friction moment is defined as Mf is equal to minus minimum micro n plus FFR and F maximum tetraperiod divided by absolute tetraperiod multiplied by 1 minus e to the power of minus uh, absolute tetraperiod divided by nu is 0 divided by r multiplied by r, where tetraperiod is the relative angular velocity in the joint and r is the hinge radius supplied by the user. Normal force chapter case 1 2 normal force computed through joint forces and momentum such as these equations, which of work and power loss, which of work contribution from the total friction moment is obtained through a multiplication by variation of the relative rotation between the two parts. Delta W is equal to mf delta theta. The energy dissipation rate caused by the friction moment can be written as QAF is equal to minus MAF multiplied by tetraperiod. In cylindrical joint, most of the theory is the same as for the hinge joint. Any differences are described here. Friction force and moment. The total friction force and total friction moment are defined as FF is equal to minus minimum micro m plus FFR plus, and F maximum sinus lambda multiplied by 1 minus e to the power of minus absolute u prime divided by nu 0 mf is equal to minus minimum micro m plus FFR and F maximum cosinus lambda multiplied by 1 minus e to the power of minus absolute theta divided by nu 0 divided by r multiplied by r, where r is the entire cylindrical radius. Mutual work and power loss. The mutual work contributions of the total friction force and the total friction moment are obtained through a multiplication by the variation of the relative displacement and relative rotation between the two parts respectively. Delta V is equal to Ff multiplied by delta U plus Mf multiplied by delta T. The energy dissipation rate caused by friction can be written as QF is equal to minus FF multiplied by U prime minus FF MF multiplied by theta period. Screw joint. Most of the theory is same as for cylindrical joint, and differences are described here. Friction force and moment. The total friction force and total friction moment are defined as FF is equal to minus minimum micro m plus FFR and F maximum sinus lambda U prime divided by absolute U prime multiplied by 1 minus e to the power of minus absolute u prime divided by nu 0 mf is equal to minus minimum and the parenthesis mixture n plus ffr and fm maximum cosinus lambda multiplied by u prime divided by absolute u prime multiplied by 1 minus e to the power of minus absolute tetraperiod divided by nu is 0 divided by r multiplied by r. Tangential lambda is equal to np divided by 2pr, where n is the number of stars, p is the pitch, and r is the screw radius. Normal force, case 1, 1. The normal force computed from the attachment reaction force is N is equal to sigma FR multiplied by N plus sigma FR multiplied by E multiplied by cosinus lambda. Case 1, 2. The normal force computed through joint forces and moment is equal to N is equal to absolute Fj minus Fje multiplied by E plus absolute Fj multiplied by E cosinus lambda plus absolute alpha 12 multiplied by mj 12 plus absolute alpha 13 multiplied by mj 13. Planar joint. Most of the theory is same as the prismatic joints. Any differences are described here. There are two ways to model the friction forces in a planar joint. In the first approach, the total friction force is applied at the center of joint. This is similar to other joint types, but in this approach, no friction moment is caused by the relative relation. In the second approach, the distributed friction forces are applied on the selected boundaries, and hence there is an effective friction moment on for relative rotation. Friction force, total force at the center of joint. The total friction force is defined as Ff is equal to minus minimum micro m plus FFR and FF maximum U prime R divided by absolute U prime R multiplied by 1 minus e to the power of minus absolute U prime R divided by nu 0, where U prime R is the relative velocity vector in the joint. Friction force distributed force on selected boundaries. The distribution friction force is defined as FF is equal to minus minimum meter n plus FFR and FF maximum multiplied by U print RT divided by absolute U print RT multiplied by R multiplied by 1 minus e to the power of minus absolute U print RT divided by nu is 0. URT is equal to UR plus R destination minus R source multiplied by x minus xc, where x is the material coordinates on the selected boundaries. Xc is the center of the joint and R is the total contact area. Normal force. Case 1, 2, the normal force computed through joint forces and moments is equal to N is equal to absolute FJE plus alpha 12 MJ12 plus absolute alpha 13 MJ13 virtual work and power loose total force at center of joint. The virtual work contribution from the total friction force is obtained through a multiplication by the variation of the relative displacement vector between the two parts. Delta W is equal to FF multiplied by delta UR. The energy dissipation rate caused by friction can be written as QF is equal to minus FF multiplied by UAR. Thank you so much for watching my tutorial video until the end. Today is the 9th day of the June 2026. Time is 9:01 p.m. Also, you can download the proper and appropriate capsule multiphysics simulation file from my github.com/masterscript.